Calculus with Polar Coordinates. Let's first review how to find the area of a sector. Suppose we have a piece of a circle here with a central angle of theta and a radius of r. We know the area of this is 1/2 r squared times theta. And of course, theta must be measured in radians. Let's talk briefly about where this comes from. So we know that if we have a circle of radius r, the area of the circle is pi times r squared. Now let's suppose we create a central angle theta, and we want to find the area of this portion of the circle, which is called a sector. To get this area, what we need to do is figure out how much of the entire circle is this section. Well, we know that there are 2 pi radians in a circle, and so this is going to be theta out of the 2 pi. So we have theta divided by 2 pi. This is the percentage of the circle. Multiply that by the area of the circle, and then we can cancel the pi's here, and we end up with theta times r squared divided by 2. And of course, that is the same as 1/2 r squared times theta. Now let's talk about how this applies to finding the area in polar coordinates. Suppose we have some function r equals f of theta, and we would like to find the area between theta equals a and theta equals b. Notice that we don't say find the area under the curve. So we are no longer finding the area between the curve and the x-axis like we've done so often in the past. Now, because we're in polar coordinates, we are between the angle A and the angle B. And so this naturally creates sort of a sector-shaped graph. So how we find this area is, of course, we divide it up into a bunch of subintervals. And then if I take a look at one of these intervals here, I can approximate the area inside of here by finding the area of this sector. And of course, we know the area for this sector is 1/2 r squared times theta. R is the radius here, which we're going to call f of theta I. And then the angle theta is actually this very small angle here, which we're going to call delta theta. And so the area of this small sector here is going to be the area of the ith sector is 1/2 times r squared, which is f of theta I star, quantity squared, and then times delta theta. And that's what you see inside of this summation here. And so to get the area inside of this curve, we are going to add up all of the areas of these little sectors here. And that's why you see the sum from I equals 1 to n. And then, of course, if we take the limit of this, it turns into an integral. And so to find the exact area between A and B under a curve f of theta, it is the integral from A to B, 1/2 f of theta quantity squared times d theta. And if we view r as f of theta can be replaced with r, and we simply get 1/2 r squared d theta, integral from A to B. All right, so let's apply this to an example. Find the area enclosed by one loop of the 4-leafed rows r equals the cosine of 2 theta. So I've taken the liberty to show you the graph of r equals cosine of 2 theta. It is this flower-shaped graph that you see here, and it is traced out exactly how I am tracing it out now. And we want to find the area enclosed by one loop. So that is this area here. Now, the most challenging part of finding the area is finding the limits of integration. So we know the area is going to be the integral from A to B of 1/2 f of theta quantity squared times d theta, or we can say the integral from a to b of 1/2 r squared d theta. And in this case, we know that r is cosine of 2 theta. So it's simply the integral from a to b of 1/2 cosine of 2 theta quantity squared d theta. But the big question is, what are the limits of integration? Where do we start and where do we end? Now I know you can see here on the graph that we have some suggested values, but how do you figure those out if you're not looking at a graph? So to do this, what we'll need to do is just make a quick table of values. So r is equal to cosine of 2 theta. Let's say if theta is 0, r is going to be the cosine of 2 times 0, which of course is equal to 1. And that would be this point right here. So this is when theta equals 0. And let's plug in pi over 4. At pi over 4, r is going to be cosine of 2 times pi over 4, which is cosine of pi over 2, which is 0. And so that is this point right here. So we can see from theta equals 0 to theta equals pi over 4, we have this portion of the graph. Now, if we integrate using those limits, if we just go from 0 to pi over 4, what we're going to find there is this area. And that's actually fine, because if we want the area of this whole thing, all we have to do is multiply that by 2. So when you have symmetry, I would advise using that symmetry. Now it is true that this point down here corresponds to theta equals negative pi over 4. And so you can integrate from negative pi over 4 to positive pi over 4, and then you would not have to multiply by 2. But I like using symmetry because it is really nice to have one of your limits of integration be 0. So now let's go ahead and perform the integration. So we have 2 times 1/2, those are going to cancel out. So we just get the integral from 0 to pi over 4 of cosine squared of 2 theta, d theta. And now I'm just going to apply the trig identity. Cosine squared of 2 theta is 1 plus the cosine of 2 times 2 theta, which is 4 theta, divided by 2, d theta. Of course, we can pull out the 1/2. Like so. And now we'll go ahead and take the antiderivative. And so what we've got here is 1/2. The integral of 1 with respect to theta is theta. The integral of cosine of 4 theta is 1/4 sine of 4 theta. And this goes from 0 to pi over 4. Now when we plug in pi over 4, we're going to have pi over 4 here plus, now let's think about what happens when you plug in pi over 4 here. Plug it in pi over 4, we have 4 times pi over 4, which is pi, and the sine of pi is 0. Minus, and then we're going to plug in 0 into here and into here, and of course when you plug in 0 to both of those, you are going to get 0. So pretty nice math in the end. This ends up just being 1/2 times pi over 4, which is pi over 8. Now let's talk about how to find the area between two curves, and also from theta equals A to theta equals B. This is fairly simple. What we're going to do is find the area underneath or inside of f of theta, which is this area here. And then we just find the area inside of g of theta. And if we subtract those two areas, we will get the area between the two. So the way we find the area between two curves is we take the area underneath or inside of the first curve minus the area inside of the second curve, and we can put these together into the following formula. So just understand that f of theta is the outside curve and g of theta is the inside curve. So for our next example, we wish to find the area of the region that lies inside the circle r equals 3 sine of theta. and outside the cardioid r equals 1 plus sine of theta. Now please understand that in order to find these areas, you will often have to sketch a graph of each of these. Now we've already talked about how to graph 1 plus the sine of theta in a previous video. 3 sine of theta is pretty simple to graph. It just ends up being a circle that you see here. And so if we want to find the area that lies inside of the circle, but outside of the cardioid, we are talking about the area in between that you see here. So again, the biggest challenge here isn't graphing or looking at the outside or inside curves. It's finding the limits of integration. Now you can see the limits here. They're listed as pi over 6 and 5 pi over 6. But how do we know that? Well, what you need to do is set the curves equal to each other. So we have to take 3 sine of theta and set it equal to 1 plus the sine of theta. And then we solve this equation by subtracting sine of theta from both sides. This gives us 2 sine of theta is equal to 1. Dividing by 2 gives us sine of theta is equal to 1/2. And from here, we know that sine is 1/2 at pi over 6 and 5 pi over 6. These are considered fundamental values that we should know. So now to find the area in between the two, we're going to have 1/2 the integral from pi over 6, that is this point here, all the way over to 5 pi over 6 of the outside function squared, so that's 3 sine of theta quantity squared, minus the inside function squared, and that is 1 plus sine of theta quantity squared. Now again, I prefer to use symmetry whenever I can, so I would like to point out that the area here is obviously the same as the area over here due to symmetry. And we know that this angle is pi over 2. So what I can do is I can change this limit to be pi over 2, and if I do that, I'm going to have to multiply by 2, because then I'm finding only half of the area. So I'll need to multiply by 2 for the final result. So let's go ahead and apply that. So this becomes the integral from pi over 6 to pi over 2. Notice that the 2 and the 1/2 cancel out. We have 9 sine squared of theta minus, and now we have to square 1 plus sine of theta. Now if you take your time and multiply 1 plus sine times 1 plus sine, you'll find that you get 1 plus 2 sine of theta plus sine squared of theta. Next, we'll distribute the negative sign. And let's just point out that 9 sine squared minus 1 sine squared is going to be 8 sine squared. And then we have minus 1 and then minus 2 sine of theta, d theta. And again, this goes from pi over 6 to pi over 2. Now, remember, to integrate sine squared or cosine squared, just like in the previous example, we need to use a half-angle identity. So we need to know that sine squared of theta is 1 minus the cosine of 2 theta divided by 2. So 8 sine squared is going to be 8 times this, and that will be 4 times 1 minus cosine of 2 theta, which is 4 minus 4 cosine 2 theta. So I can replace 8 sine squared with this expression. And so this becomes the integral from pi over 6 to pi over 2 of 4 minus 4 cosine 2 theta minus 1 minus 2 sine of theta d theta. Now, just a little bit more simplifying here. We have 4 take away 1, that is 3. And of course, you could skip some of these steps if you notice some of these simplifications a little bit earlier. But here is what we have. Now we should be ready to go ahead and take the antiderivative. So the antiderivative of 3 is 3 theta. minus 4 times the antiderivative of cosine of 2 theta is 1/2 sine of 2 theta. And then minus 2 times the antiderivative of sine is negative cosine of theta. And again, we're going to apply our limits of integration here. Let's clean this up a little bit. So we have 3 theta minus 2 sine of 2 theta, and then plus 2 cosine of theta. Okay, so now we just need to evaluate this. So plugging in pi over 2, we are going to have 3 times pi over 2 minus, when you plug in pi over 2 here, you're going to get sine of pi, which is 0. And when you plug in pi over 2 here, you get cosine of pi over 2, which is also 0. This is why we prefer to change the limit to pi over 2. Minus, now we're going to plug in pi over 6 here, so that gives us 3 times pi over 6. And then we have minus 2 sine of 2 times pi over 6, which is going to be pi over 3. And then plus 2 cosine of pi over 6. Now we need to figure those out, but this is going to give us 3 pi over 2 minus 3 pi over 6. And then we have minus minus, which is plus 2 times the sine of pi over 3 is radical 3 over 2. And then we have minus 2 times cosine of pi over 6, which is 2 times radical 3 over 2. And so this is interesting. These cancel out, and we end up with 3 pi over 2 minus pi over 2, which is 2 pi over 2, which is pi. Now let's find the area that lies inside the first curve and outside the second curve. The first curve is r equals 1 plus cosine of theta, and the second curve is r equals 2 minus cosine of theta. Now these are both cardioids, and so to graph these, we should be able to get a reasonable graph just by plugging in the quadrantal angles. So for 1 plus cosine of theta, let's plug in theta equals 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now you can pause the video and figure these out if you want, but when you plug in 0, you're going to get 2. Plugging in pi over 2 is going to give you 1. Plugging in pi gives you 0. 3 pi over 2 is going to give you 1, and 2 pi will give you 2. And then we do the same thing for the other one here. We're going to plug in these same quadrantal angles. Plugging in 0, we will get 1. Plugging in pi over 2, we get 2. Plugging in pi, we're going to get 3. 3 pi over 2, we get 2. And 2 pi, we will get 1 again. And now I'm just going to put these points on a graph. So here are the points from the first curve, and this is going to be a cardioid, which looks something like this. It's very similar to an earlier cardioid that we graphed, except that this one is horizontal. And then the other graph here, we're going to have a point at 1, 0, a point at 2 pi over 2, 3 pi, 2, 3 pi over 2, and 1, 2 pi. And this one is going to have a very similar kind of shape. And now remember, we want to find the area that lies inside of the blue curve, which is in here, and outside of the red curve. So here's the red curve. So inside the blue and outside the red is going to be this area right here. So the next thing we need to do is we need to figure out, where do these curves intersect? What is the value of theta here, and what is the value of theta here? And of course, we can't just look at my graph to determine this, because my graph is not an exact picture. What we need to do is take these two curves, r equals 1 plus cosine of theta and r equals 2 minus cosine of theta, and we need to set them equal to each other. And if we do that, we're going to end up getting 2 cosine of theta is equal to 1, or cosine of theta is equal to 1/2. And in the first quadrant, this occurs when theta is pi over 3. And in the fourth quadrant, this occurs at negative pi over 3. Now, please note that I could have said 5 pi over 3, but we want one continuous interval here. So we're going to say negative pi over 3 for this angle and pi over 3 for the other angle. And indeed, you can see that my graph is not very good because they should have intersected out here if I had graphed them perfectly, but I did not. But that's why we don't rely on pictures. We have to rely on algebra to give us precise values. Now, one other thing that I'll point out is to find this area here, all I really need to do is find the area here, which would be the area between 0 and pi over 3, and then just multiply that area by 2. So let's go ahead and do it that way. So we know that the area is going to be 2 times, and then the area formula is 1/2 integral, in this case from 0 to pi over 3, and then we're going to have the outside curve. So the outside curve is the blue curve, which is 1 plus cosine of theta, quantity squared, minus, and then the inside curve is 2 minus cosine of theta, quantity squared. So now the whole problem comes down to figuring out this integral. Of course, 2 times 1/2 is going to cancel out, and so we end up getting the integral from 0 to pi over 3, 1 plus 2 cosine theta plus cosine squared theta, minus, and then the second one, when you multiply it out, is 4 minus 4 cosine theta plus cosine squared theta, d theta. Now, when we distribute the negative sign here, something happens. Cosine squared minus cosine squared cancels out. For the numbers, we are going to have 1 take away 4, which is negative 3. 2 cosine theta minus 4 cosine theta is positive 6 cosine theta. Again, we're going from 0 to pi over 3. And now this is a fairly straightforward integration problem. We have the antiderivative of negative 3, which is negative 3 theta, plus 6 times the antiderivative of cosine, which is sine. And we are going from 0 to pi over 3. Plugging in pi over 3, we have negative 3 times pi over 3, plus 6 times the sine of pi over 3, minus, and then of course when you plug in 0, you are going to get 0. And so we end up with negative pi plus 6 times the square root of 3 divided by 2. This is the same as 3 radical 3 minus pi. Now suppose we wish to find the length of the arc between A and B. So instead of finding the area, now we are interested in finding out how long is the curve from here to here. Well, it turns out that the formula is given here. L equals integral from A to B of the square root of the quantity r squared plus dr d theta squared d theta. Let's talk about where this comes from. So we know that r is equal to f of theta, but we also know that we can write the parameterization for this function by simply using x equals r cosine of theta and y equals r sine of theta. But if r is equal to f of theta, we can replace r here with f of theta, and we can replace r here with f of theta. And this becomes f of theta cosine of theta, and the other one is f of theta sine of theta. Now, we already know that if we're using parametric equations, the arc length is given as the integral from a to b of the square root of dx d theta squared plus dy d theta squared with respect to theta. This is the arc length in parametric form. So all we have to do now is find dx d theta. So dx d theta, notice that you have a product of two functions of theta. And so dx d theta will be the first function, f of theta, times the derivative of the second function, cosine of theta, and the derivative is negative sine of theta, plus, and then we have the derivative of f of theta multiplied by the second function, which is cosine of theta. And dy d theta can be found the same way by using the product rule, and that's going to give us f of theta times cosine of theta plus f prime of theta times sine of theta. And so now let's figure out what is dx d theta squared plus dy d theta squared. And the reason I'm interested in that is because that is the expression inside of here. So let's clean this up a little bit. Dx d theta is this thing here, which I'm going to write as f prime of theta cosine of theta minus f of theta sine of theta. We are going to square that. Plus, and then dy d theta, all right, in the same flavor. And we are going to square that. Now we just have to do a lot of algebra here. So imagine writing this down twice, multiplying it by itself, and doing the same thing here. Let's go ahead and do that and come back. So here is the first one multiplied out, and here is the second one multiplied out. Now we're going to add these together, and I want you to notice that these cancel each other out. And for the rest of them, I'm going to add these two together, and I'm going to factor out f prime of theta squared. So if I do that, I'm going to have f prime of theta squared times cosine squared plus sine squared, plus, and then when we add these together, I will factor out f of theta squared, and we will have sine squared of theta plus cosine squared of theta. But of course, these are both equal to 1. And so we end up with f prime of theta squared plus f of theta squared. And f prime of theta is the same as dr d theta squared, and f of theta is the same as r squared. And that is where this formula comes from. Now let's use that formula to find the length of the cardioid. R equals 1 plus the sine of theta. So I have the graph of 1 plus the sine of theta here. We've graphed it a few times now. Now to find the length, notice that we could find the length from here to here and then simply double that length. Let's go ahead and do it that way. So here is our formula for arc length. We know that r is equal to 1 plus the sine of theta. So dr d theta is going to just be cosine of theta. Now what about the limits? So we know that when theta is equal to 0, r is going to be 1. That is this point right here. We know when theta equals pi over 2, r will be 2. That is this point up here. So we know that if we go from 0 to pi over 2, we will capture this arc length. But to get the rest of this arc length, we have to actually take it backwards to negative pi over 2. And if we go back to negative pi over 2, you'll see that r is 0. So to get the length, we will do 2 times the integral from negative pi over 2 to positive pi over 2. And then we have the square root of r squared, which is 1 plus sine of theta quantity squared, plus dr d theta squared, which is cosine of theta quantity squared. And now we just need to do the math here. So this is going to give us 2 times the integral, same limits, square root of 1 plus 2 sine of theta plus sine squared theta plus cosine squared theta d theta. This looks very familiar. We have 1 plus 1 there, which is 2. So this becomes 2 times the integral of the square root of 2 plus 2 sine of theta. Now I say this looks familiar because we had a similar integral in a previous video lesson. Let's talk about what we did there. So the next step is going to be factoring the 2 out of the radical. So that is going to give us a radical 2. And we'll pull that outside the integral with the 2 that we already have there. And then pulling out that 2 leaves us with 1 plus sine of theta under the radical. So what we need to do now is remember that we have an identity. 1 plus sine of theta. Actually, I take that back. We do not have an identity. I was thinking 1 plus cosine of theta. We have an identity for that. We have a half angle identity. For this one, we have to apply an algebraic manipulation. So if I have the square root of 1 plus the sine of theta, I can write that over 1, and then I'm just going to multiply by the square root of 1 minus the sine of theta to the top and to the bottom. And in doing that, we will get the square root of 1 minus sine of theta in the bottom. And then on the top, we will have the square root of 1 minus sine squared of theta, which is actually the square root of cosine squared of theta. And of course, the square root of cosine squared is cosine. So we can rewrite this integral as 2 radical 2, integral from negative pi over 2 to positive pi over 2. And then we've got cosine of theta divided by the square root of 1 minus the sine of theta, d theta. Now this requires a u substitution. I'm going to let u equal 1 minus sine of theta. du will be negative cosine of theta d theta. We'll put a negative here and a negative here. And this is going to become negative 2 square root of 2 integral square root of u in the denominator, du on top, and then the new limits of integration are going to be 2 and 0. And of course, we can switch those around to 0 and 2. Write this as u to the negative 1/2 times du. And doing the math here, we get u to the 1/2 divided by 1/2, which is 4 radical 2 square root of u from 0 to 2, which is 4 radical 2 times radical 2, which is 8. Now, I'd be not fully honest here if I didn't point out the fact that when you plug in pi over 2, the denominator here is 0. So technically what you're supposed to do here is take a limit as theta approaches pi over 2. Now the reason that ends up not being an issue is because when you take the antiderivative of this, the negative exponent turns into a positive exponent. And so that expression is no longer in the denominator of the fraction. But technically you should be using an improper integral here. All right, the last thing we're going to talk about here is the slope of a tangent line in polar coordinates. So we know from our earlier discussion that if we write x equals r cosine of theta and y equals r sine of theta, and if we know that r is equal to f of theta, we can replace r with f of theta. And then we can do dy dx by using the derivative formula for parametric equations. So dy dx is dy d theta divided by dx d theta. So what is dy d theta? Well, again, remember, to do dy d theta, you have to use the product rule here. And so what I have is first times derivative of the second plus the second times the derivative of the first. So it looks something like this. And then dx d theta, I can do the same thing. First times derivative of the second plus the second times the derivative of the first, And if we switch the order on both of these and plug them in to here and here respectively, we end up with the following formula. So dy dx is equal to dr d theta times sine of theta plus r times cosine theta, all divided by dr d theta times cosine of theta minus r times sine of theta. Let's take a look at an example. So for the cardioid, r equals 1 plus the sine of theta, the same one we looked at in example 4, find the slope of the tangent line when theta is equal to pi over 3. So let's just focus on that one first. So to find the derivative, we know the formula dy dx is equal to dr d theta times sine of theta plus etc. and divided by the rest. So we're going to start by just rewriting r is equal to 1 plus the sine of theta, and we could find dr d theta using regular derivative techniques, and we know that this is equal to cosine of theta. So dy dx is going to be dr d theta, which is cosine of theta, multiplied by sine of theta, plus r, which is 1 plus sine of theta in this problem, times cosine of theta, all divided by dr d theta again, which is cosine of theta, times cosine of theta, minus r, which is 1 plus sine of theta, times sine of theta. Now let's do a little bit of simplifying here. We have sine of theta, cosine theta, plus we have 1 times cosine, which is cosine, plus sine times cosine, which is sine times cosine, divided by, in the bottom we have cosine squared theta, minus 1 times sine of theta, and then minus sine times sine, which is sine squared of theta. So a little bit more simplifying we could do in the numerator is combining like terms. We have 2 sine of theta, cosine of theta, plus cosine of theta, all divided by cosine squared theta minus sine of theta minus sine squared of theta. So this is our dy dx. Now we want to find the slope of the tangent line when theta equals pi over 3. So to do this, to find the slope, we just need to take our derivative dy dx and evaluate it when theta equals pi over 3. So we simply need to plug pi over 3 into our derivative. So if we do that, we're going to have 2 times the sine of pi over 3 cosine of pi over 3 plus the cosine of pi over 3 divided by cosine of pi over 3 quantity squared minus the sine of pi over 3 minus the sine of pi over 3 quantity squared. This is 2 times the sine of pi over 3 is the square root of 3 over 2. Cosine of pi over 3 is 1/2 plus cosine of pi over 3 is 1/2 again. Cosine of pi over 3 is 1/2 again, and that is squared, minus the square root of 3 over 2 minus the square root of 3 over 2 quantity squared. So now if we simplify this, we can do some canceling here. The 2's cancel. And in the numerator there, we have radical 3 over 2 plus 1/2. And in the denominator, 1/2 squared is 1/4 minus radical 3 over 2 minus, and then radical 3 over 2 quantity squared is 3/4. And so we end up with radical 3 over 2 plus 1/2 divided by negative radical 3 over 2 minus 1/2. So next step here is I'm just going to multiply the top and bottom by 2. This will give us radical 3 plus 1 divided by negative radical 3 minus 1. And the last step here, I'm going to rationalize the denominator. Actually, no, I can do this in a much simpler way. Never mind that. I can factor out a negative in the denominator. And will you look at that? These cancel out. And so what we have on top is a 1, and in the bottom we have a negative 1. And so the slope of the tangent line is negative 1. Okay, let's take a look at part B. For part B, it says find the points on the cardioid where the tangent line is horizontal or vertical. So let's remind ourselves what the derivative is. And for the tangent line to be horizontal, we need the numerator of the derivative to equal 0. And for the tangent line to be vertical, we need the denominator to be 0. Now, I would like to take the liberty to simplify this a little bit more. Let me factor out a cosine of theta on top. And this will give us 2 sine of theta plus 1. And in the denominator, I'm going to change cosine squared to 1 minus sine squared. And so that denominator becomes 1 minus sine squared is 1 minus 2 sine squared, and then minus sine of theta. And so I can rewrite that as negative 2 sine squared of theta minus sine of theta plus 1. And then we can factor a negative out. And if we pull a negative out, it's going to look like this. And then from there, we can factor the rest of that. So let's go ahead and write this down, and then you can decide if you agree or not. Okay, but it should factor like this. Now, for the horizontal tangent, we know that dy dx must be equal to 0, which means the numerator must be equal to 0. And this means either cosine of theta is 0 or sine of theta is negative 1/2. And cosine is 0 at pi over 2 and 3 pi over 2. And sine is negative 1/2 at 7 pi over 6 and 11 pi over 6. And again, these are fundamental values, so I'm not going to do a whole lot of explaining here. Let's go ahead and take a look at the vertical tangent. So for this, dy dx needs to be undefined. And to be undefined, it means that the denominator has to be 0. So negative quantity 2 sine of theta minus 1 times sine of theta plus 1 needs to be 0. And for that to happen, we need to have sine of theta equals 1/2 or sine of theta equals negative 1. Now sine is 1/2 at pi over 6 and 5 pi over 6. And sine is negative 1 at 3 pi over 2. So I want you to notice that both the numerator and the denominator are 0 at 3 pi over 2. So that means we don't yet know if we have a horizontal or a vertical tangent at 3 pi over 2. We know we have a horizontal at pi over 2, 7 pi over 6, and 11 pi over 6. And we know we have a vertical at pi over 6, 5 pi over 6, but we do not know what happens at 3 pi over 2. So to figure this last part out, what we need to do is take a limit as theta approaches 3 pi over 2 of our derivative, which is this. What does this equal? Well, what we can do is break this up into the limit of 2 separate things. We can take 2 sine of theta plus 1 divided by 2 sine of theta minus 1, and we'll include the negative on that. And then we could multiply that by the limit as theta goes to 3 pi over 2 of cosine of theta over sine of theta plus 1. Now, why am I doing this? Well, it's because this is where you get the 0 divided by 0 from. So this limit we can evaluate by simply plugging in 3 pi over 2. So if we plug in 3 pi over 2, we're going to get negative 2 times the sine of 3 pi over 2 is negative 1 plus 1. And then in the bottom we have 2 times the sine of 3 pi over 2, which is negative 1 minus 1. And this is simply going to be negative 1 divided by negative 3, and that is going to end up being negative 1/3. But then we have to multiply that by this limit. And this limit we know is 0 divided by 0. So to do this one, we have to apply L'Hopital's rule. We're going to take the limit as theta goes to 3 pi over 2. We'll take the derivative of cosine, which is negative sine. And then we'll take the derivative of sine, which is cosine. And now you see that this limit is going to be negative 1 divided by, and then cosine is 0. And so what we're getting here is infinity. So we have negative 1/3 times infinity, which essentially is negative infinity. But actually, if you do a two-sided limit, one from each side, you'll find that one side goes to infinity and the other side goes to negative infinity. So we definitely have a vertical tangent at that point. Okay? So we know that 3 pi over 2 is not horizontal, and it belongs in the vertical category. And just for confirmation, I'll bring in a graph here. So I want you to notice at pi over 2, we have a horizontal tangent. At this point here, which is 7 pi over 6, we have a horizontal tangent. At this point here, which is 11 pi over 6, we have a horizontal tangent. So that confirms all of these. And then at pi over 6 is right here. We have a vertical tangent there. So that confirms this one. At 5 pi over 6, we have a vertical tangent there. So that confirms this one. And of course, 3 pi over 2 is right here. And you can see that we're coming in, getting a vertical tangent at that point as well. All right, so that just confirms what we saw from our equations. And that concludes this video lesson.